Okay, so like I said, we are in the second, another group of the machine languages and grammars in Pushdown in the Chomsky hierarchy, which is Pushdown Automata. So, in terms of the Pushdown Automata, what kind of the machine it is? It is a kind of a machine, if you remember, for the finite state machine, finite state automata, FA, that we discussed last week, we have quite a different things. We have the states of the machine. We are in state A, and we have some string, which is the head of the machine. Head of the machine tries to read string one by one, and by reading each string in front of the head of machine, which it reads from the left to right, and in front of the head, when each character is read, machine switches from one state to another one. So what that's a little bit different in here for the pushdown automata. Pushdown automata has something more than the finite state machines. What is that? That's the stack. That's the kind of the memory that we use alongside we had already in the finite state automata. So pushdown automata, which they are called PDA, pushdown automatas, are a class of automata more powerful than the finite automata. And that power comes from the stack that we have in here. So when we say it is more powerful, what does it mean? It means PDAs accept a larger classes of languages than the finite automata. If you remember, we say the main purpose of the machine in here and automatas is to accept or reject strings of a language. If you remember, we said we have set of characters. From that character, we can generate lots of strings, and then we need to have a grammar to say if that specific string belongs to that language or not. And machine is something that works on the string to see if that specific string belong to the machine, to the language or not. So PDAs is more powerful than the finite automatas, and because of that, it can accept the larger classes of languages. Okay, so the next thing we need to discuss is a PDA is essentially a finite automation with an auxiliary tape on which it may. Like I said, it is very similar to FA, but the only difference is we have another thing in here which is called stack. In stack, we can read symbols, we can write symbols, and we can erase symbols. We can by read, that means we can reading something from the top of the stack. By writing the symbol, that means pushing something into the stack, and by erasing symbols, that means popping off from the stack. So the stack is last in first out. The actually the strategy and the way stack works is in the last in first out. That means the last thing you pushed inside the stack when you want to read or erase something from the stack, you read the last thing that you have already pushed into the stack. So in one word, pushdown automata is very similar to the finite automata, but the difference is the stack, and stack can work in three different ways. You can read something from the stack in LIFO strategy, you can write something into the stack, or you can erase a symbol from the stack. Okay, so the tape using the PDA is not ordinary tape, like we said. So we discussed that in here. So we need to go through more detail. So a PDA stack works on the basis of last in first. So like I said, the most recently added item must be the first one to be removed. Items below the topmost one cannot be reached without first removing items above them on the stack. That's exactly the definition of last in first out. You cannot have access to this guy until you process this guy, until you remove it, read it, and so on, blah blah. So all the time you look at the top of the stack to see what is in there. Okay, so that could be an example of pushdown automata. So that's the string we want to process with the automata. Q0 and Q1 are the state of the automata, like we had it already in the finite automata also, but we have the stack in here. So let's see what happens. You remember we used to read the strings on the tape from the left to right. So we read the first character, which is A, we are in state Q. In state Q0, reading input A with an empty stack. The stack is empty, top of the stack is nothing. The stack is completely empty. And then there is a regulation very similar to the finite automator. You remember in the finite automator we had some sort of the functions or transfer functions. Delta, if you remember, that delta used to say if you are in state Q0, if you receive A, then we will go to which state. We will have something similar in here, which we will discuss in the later slides. So what is the whole story? The story is in state Q0, reading input A and A on the top of the stack. So the function or transfer function delta in here means when you are in state Q0 and you read character A, what will happen is you will go to state Q0 again. Actually, that means you will stay at the same state, and then you push one capital A into the stack. Then we are going to read A. So what was the story? When you are in Q0, you read A, you should push one A. So that means you will push another A and you will move to the next character in the left. And then when we are in Q0, we read character B, we are in state Q1. So that's the first thing. If you are in state Q0, you read character A in here, then what will happen? You will move to state Q1. That's the first thing that happens. The second thing that happens, as you can see, one of the character capital A in the stack has been removed. So that means if you are in state Q0, you read character B, you'll take one thing from the top of the stack and go to state Q1. And again, if you are in the Q1, you receive B, you'll take one character from the top of the stack, make the stack empty, and go to in here. So what has happened here? We have finished the string. We are in the final, presumably, state, and the stack is empty. So that's another difference of the pushdown automata with the finite automata. In the finite automata will accept the string if let me check if there's any question or not. No. So in the finite automata will accept the string if you get to the end of the string and you are in the final state. That was all. But in here, you should get to the end of the string, you should get to the final state, and your stack should be empty. If still you have something in the stack, that means the string is not accepted. And if that string is generated by a language or a grammar, that means the automata doesn't accept that grammar or language. Okay, so that's very interesting and beautiful presentation of pushdown automata. So that's exactly what we discussed. Let's go to that. PDA input tape reads their input tape from left to right, to finite automata. PDAs have a finite number of internal states, finite number of queues. Okay, PDA have one start state, very similar to FA finite automatas, and it could have a set of final states. Again, very similar. So in this sense, it is completely similar to what we had in finite automata. So the transition between the state allow the top symbol of the track to be to be read and removed, added to, or left unchanged. So when you are in a specific state, you read the specific symbol of the string. You have three choices. You can read and remove something from the top of the stack. You can, which is called pop, P-O-P. You can add something on the top of the stack, which is called push, or you can left unchanged. You don't apply to the stack. So that's actually the main difference in here. Wow, all the time I touch this guy. Okay, so that's something like that. Since we have more options than just simply reading symbols, we need to have different instruction formats to FA. In the FA, you remember finite automata, we didn't have this guy, and also we didn't have this guy. We used to say if you are in state QI, you read symbol A, you go to state QJ. While here we need to say if you are in state QI, read symbol A from the tape, and you have A in your stack, you will go to state QJ, and this thing happens to the stack, which that guy means, like I said, reading and removing something from the stack, or pushing, which means pop, or pushing something to the stack, or actually leaving it unchanged. Okay, so where Qi and Qj's are states, A is a symbol of the input alphabet in front of the tape, and capital A is a symbol of the stack alphabet, which needs to be the same as the input alphabet. And gamma is a string of the symbols, whatever which is in the stack. Okay, so we don't need to go through interpretation because I discussed that. So again, instruction Qi, A capital A, Qj, gamma results replacing A with a string Q gamma. For example, if gamma is empty, the empty string, then A is removed. So that means you're from in state Qi, receive string A, character A, and you have A inside the stack, capital A. If you go to empty, that means you are removing. If that gamma is B, that means you remove A, pop A, and push B instead. So if the stack had only one character, that means you get rid of A and push B instead. And if it is BC, then A would be removed and BC is added to the top of the string. So you can push more than one character at the same time. That means another example, if gamma is A, the transition would leave the stack unchanged. Okay, so that's the whole story of the instruction in Pushdown Automata. Okay, so PDA instruction with empty stack string. Okay, so if the stack string in the interpretation is empty, then the transaction does not depend on the content of the stack, since epsilon can always be read at the top of the stack, whatever it may actually contain. Okay, that's a very interesting concept. We will see what does it mean. Note that empty or epsilon here does not include the stack must be empty. So what does it mean? It means if I'm in a state Qi, if I read character A from the head of the string, and then if that means whatever. That means whatever is on the top of the stack in here. So for example, if that happens, that's true. That means I'm in a state Q0. Actually, that's A. Imagine we are in here. And I'm reading A. So on the top of the stack is A. That's okay. If it is B, that's okay. If it is empty, that's okay. So this expression means if I'm in a state Qi, if I read A and whatever it is on the top of the stack, I will go on to state Qj and I will push something, I will do something with the stack. Okay, so that's the most important thing you need to take into account in here. So epsilon doesn't mean stack should be empty. So this doesn't mean if you are in state Qi, read character A, the stack is empty, go to here. No, it means if you are in state Qi, read character A, and whatever is on the top of the stack and do these things. If we had, for example, the transition would push B into the stack like we discussed. Okay. The starting and ending computation. At the beginning of a computation, the stack is assumed to be empty. So when you want to process a specific string with the PDA, you assume the stack is empty. PDA is in the initial state, and the reading head is positioned over the leftmost symbol of the input. That's very similar to the FA. That's very similar to the FA again. And that's the new thing we have in here. The stack should be empty. And an input tape is accepted if the computation leads to a situation in which all the three of the following are simultaneously true. So that means the PDA will accept a specific string if the entire input has been read, you have finished the string, the PDA is in the final state, you have completely finished, you have reached the final state. Like I said, we can have more than one final state in here, very similar to FA, and the stack is empty. Now, note, you can also define acceptance by either the empty stack or final stack or both, and the resulting classes of automata turn out to be equivalent. So that's a very good thing also in here to consider. Okay, so we can define a PDA using this set of things. If you remember, we used to do that for the finite automata too. Okay, so for example, if that's a language in here, the following is an example of PDA which accepts the language A and B and n greater than 0. What does it mean? What kind of a language? What sort of the string this language generates? That means n should be greater than 0, 1, 2, 3, and so on. So that means A1, B1, that means AB. What is the string for N2? It is A2, B2. You know, we don't have a square in the strings of the languages. When it is A2, that means AA. When it is B2, that means BB. So we have A2, B2, that means we have A, B, B. Another string would be A, B, B, B. Okay? So that's a language, and this language is accepted by PDA. What are the definition of this PDA? First of all, the states are Q0, Q1. We have two states. And then the alphabet of the language is AB. And the set of the thing that we have for the stack or stack alphabet, it is capital A. Initial state is Q0. And we have two final states. And that's the transitions. If we are in state Q0, we receive A. No matter at which state, what we have on the top of the stack, we will go to state A. We will remain in state Q0 and we will push A into the stack. If you are in Q0, receive B, we have A on the top of the stack, we will go to Q1 and we can do anything. We can push, we can pop, or we can leave it unchanged. If we are, sorry, that's empty, that means we will remove, we will pop one character from the stack. And if we are in Q1, we will read 1B, and we have A on the top of the stack, and then what happens, we will stay in Q1 and we will remove another character from the top of the stack. Okay, so if we want to see if this language is accepted by this automata, let's see what is the next slide. Okay, we have it here. We don't need to talk about that in here. So that's the transition then. We discussed that. We want to see this specific string of this language is accepted by this automata or not. This language, and that's one of the string that can be generated by that language. We want to see if that machine, if that PDA accept this language or not. We should check to see if this language, this automata accept this string or not. Okay, let's see what happens. Okay, we have this string, we want to check it. We start from state Q0 because according to the definition, the initial state is Q0. Okay, we are in Q0, we read A, and that's the transition. It says when you are in Q0 and read A, no matter what you have in the stack is empty in the beginning, push 1A. I'll push 1A. 1A will goes into the stack. I'll head of the machine will goes to the next, will goes toward the right and reads the next symbol. The next symbol is A. We have Q0. We are in state Q0. We have character A. So still we have this rule. We don't have any other rule which says we are in state Q0 and read A. That's the only rule which says if you are in state Q0 and you read character A. Okay. So we read character A, and no matter what is in it, and then you will push another A. I will push another in here and move to the right side. Then I am in state Q0. I read B, Q0B, and that's the only rule which help us. Okay, I'm in state Q0, read B. What does it mean? It means please pop one character from the top of the stack. So I will take this A from the top of the stack. I will empty A. I will have one A in the stack. I will move to state QA. Okay, and I have another character. Move to the last character. Then I'm in QA, read B. I'm in QA, read B. And then if you are in QA and read B, and if you have A on the stack, okay, everything is okay. The state QA1, reading B, I have A in the stack. What happens? I will stay in QA and I will take one character from the stack. I stay Q1 and take one thing from the stack. What happened in here? I finished the string. I am in a final state and the stack is empty. All the criteria are justified and satisfied. Then that means the string accepted. Okay, so that was one situation to see what has happened. And there is a good interpretation in here if you look at the whole thing that has happened, machine has gone through. See, by reading A, that means I push A into the stack. So I have two A's, that means I have pushed two A into the stack. Imagine that as your packet and consider these guys as a coin. So that means whenever you read A, you will put one coin in your pocket. You have two A's, you have read two coins into your pocket. And then B is a situation where by reading any B, you will take off one coin from your pocket. So you have two B, that means you empty your pocket completely. You start with an empty pocket, you read the string, and you're adding coin to your pocket, and you start removing coin from your pocket, and you finish with an empty string. So that's another good interpretation that shows how you should look at the PDAs, and will get you some, intuition. It will get you some understanding on how deal with these strings. Okay. What about this string? Is it accepted with this machine? It should be okay. It should be, is this string is accepted? So what was the story? The story was, if you have B, you should take one coin from your packet. Okay, so does it mean? It means if you start with B, you should take one from your packet. But in the beginning, you start the string, your packet is empty. How do you want to take one coin from your packet? How do you want to take one string, one character from the stack? It is impossible because the stack is empty. So we don't have any regulation for being in Q0, reading B, and a stack is empty. So we don't have any rule for that. So definitely it is rejected. It's not accepted. What about this one? So you have 3A. That means you will put three coins in your pocket. The first coin for this guy, the second coin for this guy, and the third coin. Okay, and then you will take off two coins from your pocket, and still there is one coin inside your pocket. That means the machine won't accept this string of the language, right? So that's a problem. It is rejected. What about this one? That's the same situation. You will put two coins into your pocket. You will take 2 coins of the pocket. Pocket is empty, but still you have another string. You are not at the end of your string. You have another symbol, and you don't have anything inside your pocket to take off to get an empty string and finish it, empty stack and finish the string. So it is rejected then. What about this one? That means the stack is empty. Okay, we are in the beginning state, and we don't have any character, so that's okay. We don't push anything, you don't do anything, and so on. So is it rejected or accepted? The problem is it is rejected because we cannot move to define. So let me see. Sorry, finite Q0 is finite state also, so it is accepted. Yeah, so that's okay. So I don't my string is empty. I don't have any symbol. I don't push anything into the stack. I don't pop anything from the stack. I don't move to any other state. I will stay in Q0, and Q0 is a final state. So that's okay. I'm fine. So that is accepted. Okay, so this PDA works by using this stack as a counter for keeping track of the number of A's in the initial part of the input string. Once a B is found, it switches to state Q1 and begin popping an A from the stack for each B in counter. Only if the number of B's equals the number of A's will the stack be empty at the end, and it is accepted. That's another interpretation. I brought the example of the pocket and the coin. That's another interpretation. It looks at the situation as a content. Okay, that's the whole story. Okay, so very similar to the PDAs, we have deterministic and non-deterministic PDAs in here. What was the definition of non-deterministic in there and deterministic? If you remember, in finite automatas, if you have unique definition for the states, that was deterministic. Otherwise, it was non-deterministic. It looks like that's something similar. See, if I'm in state Q0, if I receive A, no matter what is in the stack, I can do something. Look at that. There is some sort of the intersection between these two guys. If I'm in state Q0, receive A, and I have capital A at the top of the stack, I can do something. This guy is the same. When it says no matter what is in there, that means A could be also on the top of the stack. So you have two definitions for this situation. So that's the reason why it is non-deterministic in here. Okay, so that's a language in here. That's a language which says if I have a string x, that x come from the AB star. What does it mean? It means you can take A or B, nothing at all, or once, or twice, or three times, or something like that. So X, for example, could be A, could be nothing, could be A, could be AA, or AB, or BB, or BA, could be three characters. That means A, and the next time A, the third time A, or A, B, B, A, whatever. What combination, what triple combination of these guys, okay? And then we have the X reverse. So for example, if it was ABB, then it would be BAA. So the language then generates characters and strings like that. So for example, if it is 3, it is A, B, A, B, A, something like that. Okay, so and this machine, the initial state is Q0, final state are these guys, and these are the regulation. This means it should reject, for example, BAPA, and this means it should accept, for example, ABBA, because this guy is not the reverse of BA, but this guy is the reverse of BA. So this machine should accept it. Okay, let's go a little bit faster. We are in the time shortage. So PDA accepting the language, initial state Q0. We have the regulation PDA above, places an image of the first of the string into the stack. Each letter reads into is pushed, and then in state Q1 we only delete stacks. See, when we are in state Q0, okay, and we receive A, we push in here. Sometimes we are in state Q0, we receive something, we can pop from it. Or when we are in state QI, no matter what, we receive A or B, and then we will pop from it. So in state Q1, we only delete from the stack. In state Q0, we either add something to the stack and stay in Q0, or begin deleting things and move to state Q1. So three things happens in state Q0. We can sometimes add something to stack like these two guys. We can sometimes stay in Q0, we don't change the situation, or we can start to delete the things and move to Q1. To check if the first part of the string is the reverse of the last part, it guesses where the start of this reverse string begins. So that means since Q1 start to pop the things from the stack, that means to finish the whole string and accept the string, we need to at some stage switch from Q0 to Q1. That's the main mission. And the language tries to check to guess where the start of the reverse string. For example, if it is reading an A with A on the top of the stack, it can either add an A on the stack and stack in Q0, or delete A from the stack and change to the removal mode. Removal mode is where we move to state Q1. Okay, changing to removal mode is only allowed at a specific point. It uses the fact that the reverse string can only start when we have just pushed letter A onto the stack and reading letter A and B. Okay, so that's the whole story of this machine. The above PDA is non-deterministic because there is more than one possible definition like we discussed. When reading A on the top on the input tape, these things can happen. That's exactly what we discussed. I don't need to go through the stories. Okay, and let's look at the situation to see what could be the state diagram conduct. State diagram, what could be the path? Let's call it path to acceptance. That's the string. I want to see if this machine accept this string or not. I'm in Q0, I receive B. What is the regulation? I take root 2. I'm in Q0, B. No matter what is the stack, I'll push 1B. I'll push 1B into the stack. I'll go to Q0, state in here. At this point, since that's non-deterministic, I have two options. I can go to any of these things. Okay, if I am in a state Q0 and receive B, that could be one option. If I'm in state Q0 and receive B, that could be another option. If I follow this path, it says push another B to the stack. I push another B to the stack, I will stay in Q0. I will stay in Q0 and push another B. And then I receive A. and I'm state Q0. I'm in state Q0, receive A, and I have B on in here. So what will happen? I use rule A. I'm in state Q0, I receive A. Okay. And why rule 3 is not used? Because rule 3 explicitly says machine should have, sorry, a stack should have A on the top, but the stack have B. So definitely we should use the rule 1. So what will happen? We will stay in Q0 and we will push another A. I have pushed another A. What is the situation? I have finished the string. I'm in state Q0, that's final state, that's fine, okay, but the stack is not empty. So the stack is rejected in this situation. Well, you remember in here we had another option. If I'm Q0 receive B, I'm Q0 receive B, this one or this one. Let's follow rule 4 in here. In 4 it says if you receive B and then go to state Q1 and take something from the stack. I'll go to state Q1 and take something from the stack. The stack had B, I'll empty the stack. Again, I'm in a final state, that's okay. The stack is empty, but the string is not finished. So that means this root even doesn't accept the string. So that's non-deterministic. Because of that, I have two different paths in here to go to the end of the string to read whole the string. I examined both of them, but none of them could satisfy the criteria I have. So that's the reason why this string is rejected. And already that is rejected. Why? Because like I said, whatever I have in here, it should be reverse of that, and that's not the reverse of the whole story. So that's the reason why we rejected in this guy. Okay, so what about the PDA above from the beginning of the lecture? Was it deterministic or non-deterministic? You remember I had the PDA like that. The states, final states are like that, and I have this transition. I'm in state Q0. If I receive A, no matter what is in it, I have a definition for that. I have an state Q0 if I receive B, and if I have A on the top of the guide, so I will go to this state, and if I'm in here, what will happen? You can tell by examining the rules. If there is only one course of action for every situation, then we call it deterministic PDA. Be careful. A rule that requires epsilon at the top of the stack will match any stack. Okay, so such rule can mean a PDA is non-deterministic, but not always. Okay, so examine it to see if it is deterministic or not, and that's a very good resolution. That means if you have a situation like this, it means probably you have multiple options for this situation, but it doesn't mean necessarily that's non-deterministic. So if you see something like that, it doesn't mean this machine, this PDA is non-deterministic, which is deterministic in this case. Okay. We saw previously that deterministic finite automata and non-deterministic finite automata are equivalent. If you remember, we said for specific languages we can have multiple non-deterministic finite automatas to satisfy that language, and we can have only one deterministic finite automata. And for all the non-deterministic finite automatas, we can have just one single equivalent deterministic finite automata. Is that the case for PDAs? No. Deterministic PDAs are not equivalent to non-deterministic PDAs. So that means if you have non-deterministic PDAs and nPDAs, it doesn't mean necessarily you should have one dPDAs in here for that. The previous example of nPDA illustration, what? There is no way to implement a deterministic PDA that accepts this guy. Okay, so that's an example that shows the whole story. So for example, for this machine, you cannot find any deterministic PDA that generates that machine, right? And there is no way when strictly reading from the left to right to know when the center of the input string has been rejected. That's a very good point. That's the main problem of this string. In this string, I have something and I have reverse of that. Why deterministic PDAs cannot work, cannot accept this string? Because the point that I should know if I have finished the first part, the first half of the string, and then I should switch to the reverse part. There is no point of that. So that's the reason why deterministic one doesn't work for it. If I want to have a deterministic rule for that, I need to add a specific character in here to say, okay, that's a specific point that I finished the first half, and then I move to the second part. If we change the language slightly and indicate a marker in the center of the string, character C, then a deterministic PDA to solve the same problem is possible. Work on this string to see if you can find a PDA, deterministic PDA, that can accept this language. It is often useful to be able to tell whether a non-deterministic language is also accepted by some deterministic PDAs. Many programming languages belong to the class of non-deterministic PDA languages. When programs are compiled, the compilation process is carried out by what is in effect a PDA. If this PDA can be made deterministic, then the process can be made more efficient by eliminating the pursuit of the alternative languages. And most programming languages in current use are in fact deterministic PDAs languages, or nearly so. Okay. And context-free grammars and languages. By far, we have talked about the push-down automatas. But you remember in the beginning of this lecture, I said for any automata or machine, we have a corresponding grammar and languages. The grammar and languages we uh, use alongside the push-down automata is context-free grammar and languages. Non-deterministic PDAs concept exactly the languages generated by context-free grammars, as known as CFGs, or type 2 grammars in Chomsky hierarchy. Also, recall that in context-free grammars, every rule is of the form. We remember what was the definition of type 2 grammar or context-free grammars. It was of this kind. In the left-hand side, you should have only one capital non-terminal character, and in the right-hand side, you can have a combination of terminal and non-terminal characters. Okay, it follows from this definition that every right linear grammar, type 3, is also a CFG. Do you remember? Type 3 grammars was kind of a subset of type 2 grammars. What does it mean? It means type 3 grammar could be considered as a type 3 grammar can be considered as a type 2 grammar, because that's a subset of that. The reverse interpretation is not correct. Any type 2 grammar cannot be considered a type 2, right? But any type 2 grammar can be that. So any regular grammar, type 3 grammar can be considered as a context-free grammar. Regular languages are said to be properly contained in the context-free languages. And so that means probably any regular language can be accepted by a push-down automata. But it doesn't mean any context-free language can be accepted by finite automata, because finite automata is related only to type 3 grammars. Context-free grammar and languages. Since non-deterministic PDAs accept exactly the language generated by context-free grammars, we can construct an equivalent like that. So we can have, do you remember for the regular grammars, we used to define them with some sort of the symbols, like the terminal, non-terminal, starting, and regulations. It was the state of the machine, and the initial state, the final state, the input alphabet, terminals, and the stack alphabet. Why it is called only the terminals? Because if you remember, in the non-terminal, in the type 2 grammars, you should have only capital A, non-terminal is in the left. And that's the reason we talk about this guys in here. Okay, and in stack, you can put only the non-terminals and terminals together. Okay, the transition or instruction of the nPDAs are constructed as follows. M contains the instructions. We have some instructions for each rule of the CFG. Contains an instruction which actually, if you have nothing, and if you have symbol A in the stack, you will go to state Q1 and have another thing in stack. That's very similar. I don't want to stay that much on that. Okay, so you can convert We used to do that exactly in the FA, if you remember. We used to convert the regulation, we used to convert the transition to the rules grammar, and we used to convert the grammars to the regulation in here. So for example, for this specific machine, if we have the transition in here, I can convert it to in here. I can say the initial state is this one, the terminal character I take is this one, and the rules is this one. If I state S, I will generate this guy. That's the definition of the context-free grammars. Or I can go to in here. You can trace it and you can see whatever you have here exactly can happen in here. Okay, so that means if I'm in state Q0 in the beginning, if I receive nothing, I will generate, and if I don't receive anything, I will, and the stack is empty, anything in the stack, I can go to state S1. The first line of transition, that means starting, that means the start. That means if I'm in Q0, initial state, I have not received anything, no matter what is in the stack, I will go to state Q1. If I'm in state Q1, I don't receive anything, any string or something, I will go to state Q1 and I will push that thing into the string. I will take this thing off and I will push this thing. That means I go from S to this one. That means I have taken S from the stack. I push this guy into the stack. That means if I had S in the stack, I now have this guy in the stack. If I'm in Q1, I receive nothing, I'm in state S, I will take that off. You can find it in here. If you are in state Q1, you receive A, and you have A in the stack, you will take this off. You can find it in here. And if you have B, and you have B in the stack, and then you can take it off. That means how to finish the stack. See, I have S in the stack, I can immediately empty the stack, or I can have this guy into the stack. I will generate this one, and then instead of S, I can put this guy and empty the stack. Right? So that's the summary. The summary is for every non-deterministic PDAs, they have some transitions. We can write a regulation, a grammar for it. And if you have a grammar of CFG, you can generate a machine to generate that language. So you can read through that yourself, but don't stay on this thing. That's the thing we discussed actually, and that's CFG and nPDA. Let's look at this guy. We have the transitions in here. We have this string, and that's the path toward to the end. I have this string. I'm going to say Q0, rule 1, Q0, whatever do you have, whatever you read, whatever you have in the stack. Whatever I read A. Whatever I have in the stack, that's empty. I will go to state Q1 and I push 1S. I push 1S in here. And then I will continue in here. So why not? Why not? Why the head of the machine has not moved 1 toward? Because that was initializing. I have not read any A. Okay, so that means this guy has happened without any string. Then I am in here. I am in state Q1. I have S in the string. That means if you are in Q1, I have S in the stack, and you don't read anything, you will push ASV. You will take S from the stack and push ASV and go to Q1. So I stay in the Q1 again. I take this A, I push that ASV, and I stay in here. Why? Because I have not read anything. And then I start to read A from here. If I'm in here and read another A, that would be rule 4. If you are in Q1, read A, and then you will have A in the stack. I have A in the stack. I'm Q1. I read A, so I will move to Q1, and I will get one thing from the top of the stack. I'll get this A from the top of the stack. So the stack would be SV. And then I'm in A, right? And I'm in Q1. I read another A. I push. I have whatever I have at the top. I have S on the top. So that guy is applied. So We don't have any regulation which in here which says if you are in Q1, you read A and S. So the only thing you can use is regulation 3. So that means I don't read anything. I'm in state S and I want to state that Q and get one of the things and push one A. Okay, so I will go this one. Anyway, since we are in the time shortage, I will finish this lecture now. So you can go through that and see how this string is generated using this guide. And you have the description in here and the description of the regulations and rules in here. So practice it yourself, and if you had any problem, please come back to me to see what's the story.